Welcome back to linear optimization. Right now we're going to perform a pivot in a Tableau. Here's an example of what we have in a Tableau. Remember, we have our basic feasible solution is here when it corresponds to this basis of variables. And I have the relative costs computed up here, and I have my current cost function negated. And what is represented in each of the columns of this main part of the Tableau is that this column vector is the representation of the jth column of A in terms of the basis columns in the order that they're given. And what we're going to do is we're going to essentially want to add xj to the basis. I want to make this variable have non-zero value when I can. It's currently got 0 value because j is not in there. So we're starting with some column which is not in the basis. That's where we want to perform a pivot. So the idea of a pivot is I want to add this column to the basis, but because that would be m plus 1 vectors, they can't all be linearly independent, and also as I increase the value, I'm going to drop one out, so it become a basic feasible solution. What we need to do is compute a value called theta 0. The way we compute this is we take the minimum of this fraction, xi0 over xij, subject to xij being strictly bigger than 0. So if I'm looking at the column corresponding to xj, what we are doing is I'm taking the value of this column, and I'm taking this entry, and I'll say, is this thing strictly positive? If it's strictly positive, take this divided by this. Okay? Take the entry of the 0th column in the first row divided by this. And I'm going to take this divided by this. And here divided by this divided by this. And what we're going to do is we're going to take the minimum such value. Okay? If this never occurs, we can think about theta 0 as being positive infinity. Okay? If this never occurs, if all of our values here are at most 0, then actually theta 0 could be infinity. And that means that our feasible set is unbounded in this direction. Okay? So what we'll do now is I'll say that once we find this minimum, when it exists, it's actually equal to some fraction. So there's some L such that this fraction is actually equal here. And L is corresponding to some basis element. So I'm looking at this row now. So we're looking at this row. That means that when I'm taking xj and I'm putting it into the basis, it's taking the place of this basis element. So what we do to mark that is we circle the Lj entry. Because this is saying xj is what I'm putting into the basis, and it's taking this position. And what we'll do is we'll now define a new basic feasible solution, and we'll modify the Tableau to reflect that. So we're going to take all the things we have and we're going to put a prime on it just to say that's representing the new value. So we can define our basis in terms of what column is the ith basis entry in. That's what this function does. And what I'll say is that's equal to the old basis entry when I is not L, this place where we pivoted, and j if I equals to L. So I've put j into the basis in the place in the Lth position. And the next thing we want to do is find our new basic feasible solution corresponding to this basis. So the x0, the ith coordinate of x0, is going to be, well, I take the old ith coordinate and I subtract how much does the jth column contributes from this basis and multiply by theta 0. That's when I is not equal to L. But when I'm actually equal to L, I'm going to put theta 0 in there. So what's happened is the previous variable that was in the basis has now been pushed all the way down to 0. But when I can do that, what we see is that these basis entries have also changed when my new variable has become up to theta 0. What's important is that Now what we need to do is to modify our tableau is diagonalize such that this element is the only non-zero entry in the column and it's equal to 1. Right? Because I want this to be the elf basis element, so this must be the elf standard basis vector. And that's what we need to do, and we'll see that in our example.